Yeah, okay. Good evening to everybody here. I'm Rishi Kumar from Saha Student Circle, as you might have already know. So, I'm going to be talking today about applications and toy models in quantum mechanics. Actually, we had a lecture on quantum foundations a few weeks back. This was supposed to be integrated with that, but since there were some time constraints, I couldn't join in. So I decided to make a separate lecture and yeah. So this is going to be a pretty short lecture. It's not very detailed as some of you might expect it to be, but sorry to disappoint. This is going to be a pretty basic overview of the fundamental applications of quantum mechanics that we have seen so far. I think in the previous lecture, we have already established a good mathematical foundation for what we are going to look into today. And so we will begin to appreciate the tools that we have acquired so far, and then how it could be used to predict some observable phenomena. And towards the end, I will be delving into a little bit of supersymmetry and its scope in revolutionizing quantum physics and particle physics as such. So then, without further ado, I'm going to be going into the first problem for all quantum physicists, which is the infinite square well. If you had taken a course in quantum mechanics so far, this is one of the first problems that you might actually end up doing, because this is the fundamental problem that it's easy and it's a good starting step for all other problems that you're going to solve, right? So then here's the premise right here. So we have this well, as we call it. Well is essentially you have these two potential barriers with potential of with infinite potential. So essentially, if you have a particle within this potential well, it theoretically or practically it cannot escape the two walls. So then the particle is said to be contained within these walls. Okay, so that is the basic premise of this problem. So one more small thing, this L right here can be substituted for A in the upcoming calculations. So yes, we must have seen what the Schrodinger equation is by now, right? So then that is equation one here, negative h bar squared by 2m, dou squared psi by dou x squared equals e psi. So, and from equation one, we can see that d squared psi by dx squared is nothing but k squared psi, where k is simply equivalent to the root of 2me by h bar. Right. So we can also see here that equation 2 is simply a simple harmonic oscillator equation. Okay. So which solutions which we have acquired previously or in the classical state situations as well, that psi of x is simply a sin kx plus b cos kx. So that is just a simple differential equation, right? So of order 2, which is easily solvable. So this a sin kx plus b cos kx is the solution that we have acquired. Okay. So moving on. So the continuity, right? So what we are going to do here is we are going to use boundary conditions to solve for K and A, K, A and B. Okay. So essentially continuity of psi of x, what does that entire um, wording mean is that essentially, as I said before, the particle cannot exist outside of x equals 0 and outside of x equals a or l. Okay, so that is the continuity of psi of x. So at psi of 0 and psi of a, the particle essentially or the quantum packet cannot exist. So then we have the probability of 0. Okay. So essentially imposing these boundary conditions into our previous equation, equation 3 here, essentially psi of x substituting for 0 here, essentially we have psi of 0 equals a sine 0 plus b cos 0, which is simply equal to b because a sine 0 is 0 and cos 0 is 1. Okay. So b equals 0, and hence we see here that psi of x is nothing but a sine kx, right? Because psi of 0 is b and psi of 0 is also 0. So now psi of A equals A sine Ka, right? Again, the simple substitution. So sine K needs to be 0, right? Because again, psi of A is 0. So which means that, so let's take that Ka needs to take these values, 0, pi, 2 pi, and 3 pi, right? From the property of the sine wave, which we must have seen before. Okay, so Ka equals 0 cannot exist because that essentially says that psi of x equals 0, and then that is non-normalizable, right? Because for any wave function, it needs to obey the normalization condition, which is equal to the entire integral from infinity to minus infinity of psi of x needs to be equal to 1. But then here, if we just take psi of x equals 0, which it is non-normalizable, so we can chuck that out. So then we only have Ka pi, 2 pi, and 3 pi. And why didn't I really explicitly mention the negative signs here? Because they're insignificant. Because if you think about it, sine of, let's say, negative theta is simply negative sine of theta. And then that negative sign can essentially be taken into our constant term A here, right? So then we don't really need that negative term to be in here. We can just use the constant to, let's say, absorb the negative sign. So then the negative solutions are insignificant. So the distinct solutions are simply kn equals n pi by a, with n taking the integer values 1, 2, and 3. Okay, so pretty simple till here. And so the possible eigenvalues of E are En equals, I think, just a second. Yeah, again, using this k here, we're just using the substitution, simple. So an E of n is simply equal to h bar squared kn squared by 2m. Again, substituting for k for this simple substitution, we get n squared pi squared h squared by 2ma squared. These are the energy eigenvalues for the infinite square well. So then what does that essentially say is that the wave function or the particle inside that infinite square well can only have these distinct or quantized values of En, right? They are not continuous. So which directly points to our quantum mechanical postulate that energy values are essentially quantized and not continuous. Okay, so this is a very nice example for that. And so now we are beginning to find out the eigenfunction of psi of x. Okay, so we can find A by using normalization, which is simply the integral of modulus of A squared sine squared kx dx is simply, this is again the normalization thing condition that I said before. Okay, pretty simple. So just using integration here, we obtain the value of A to be 2 by A. Okay, sorry, A squared to be 2 by A. Okay, so now substituting this back into our final thing right here, which is our psi of x equals A sin kx, substituting the values of A and K gives us psi n of x is equal to root 2A sine n pi by A x. Okay, so this is the eigenfunction of our infinite square well. Okay, so till now I think there shouldn't be any doubts because it's pretty simple stuff. Okay, so after this we are now entering a slightly more complicated problem, but that is again in relative terms. So the finite square well. Okay, so this is just a slightly more complicated infinite square well, and the only small difference here is that again, as the name suggests, the potential barrier here isn't infinite, right? There is some finite value of V naught. Okay, and then the rest of the premise is pretty simple. It's the same. So how are we going to solve this? Essentially, it's the same. Okay, but then we are just going to take an extra term here of V naught. Okay, and again we are starting the Schrodinger equation. Okay, so then here again looking at the diagram, we are going to look at two major cases here. One for energies below the barrier potential. So essentially, if the particle is contained in here, it cannot escape the barrier, right? Because if its energy is less than potential here, so it essentially contained within this barrier. And then the second case is if our energy of the system in concern is greater than V naught, we have some transmission occurring as well because it can cross this potential barrier. So going forward, so here we are going to look at the case with the potential less than V naught. Okay, so then first of all, we're going to take this case here for x equals less than minus a. So that is to the left here. So essentially, it's there is no potential in concern here. So we have no V naught term here. So it's just the Schrodinger equation. Okay, which is similar to the one that we saw previously, where kappa is simply root negative 2 me by h bar. Okay, so kappa is real and positive. Okay, so the general solution here to this differential equation is psi of x equals a exponential k of x plus b exponential kappa x. Okay, sorry, it's kappa. Okay, and if we notice here, this first term here, it actually tends to infinity as x increases or kappa increases, right? Because it's exponential. I think there should be a negative sign here. I'm sorry, there's some slip here. So then this term blows up, so it is not physically admissible. So the only physical admissible solution here is psi of x equals PE per kappa x. Okay. So now we're going to look at the region of negative A is less than x is greater than A. Okay, the potential V of x is simply here negative V naught. Okay, so now just substituting that into the Schrodinger equation, we get the potential here. This is again just retracing our steps, the same steps here. So we are essentially solving this differential equation, and here we are getting L equals 2me E plus V naught. So previously we didn't have a V naught term here. Here we have a V naught. Okay, and the solution for this term right here is again similar to our infinite square well potential. So psi of x equals C sine Lx plus D cos Lx. Right. So where C and D are just some arbitrary constants. You don't need to worry about that. Right. So now for the region x greater than A, the solution is very similar to x less than negative A because they're both essentially the same, but then just with a different constant. So here psi of x equals Fe power negative kappa x. All right, so far I've not solved any equations here. We just have this small collection of equations right here. And after this, we are going to solve these three equations using a similar step that we used in our infinite square well potential. So using boundary conditions. Again, the same thing, we are using the continuity of psi of x at x equals a to be Fe kappa a equals d cos La. Right? And simply differentiating this, we get our equation 19. So d psi by dx is simply just we're just differentiating this, and we got this equation here. Right? So dividing these two equations, we get kappa equals L tan La. Okay, so this is the formula for our allowed energies. Okay, so using better notation, is cleaning this up. So Z is equivalent to La, and Z naught is equivalent to A by root H. Sorry, A by H bar root 2mV naught. So just cleaning this up, we are just rewriting equation 20 in tan Z equals root of Z naught by Z whole squared minus 1. Right. So one more thing we need to note here is that why did we especially put d cos La here and not d sin La is because right here we are going to look at only the odd functions, right? The odd cases. The even cases also do exist, but I'm not going to go into that for this case alone. So then now going into our cases here. So imagine if this finite square well is very wide and it's deep, essentially V naught is very large. So then as V naught is very large, our G naught is also very large, and so our eigenvalues become almost approximate to the values we got for our infinite square will, right? But then just here is that we have a 2a squared, again, not just, I think previously if we go back, yes, we don't just have a squared right there, okay? So yeah, so for any finite potential, for any finite V naught, there are only a finite number of bound states. Unlike our infinite square, well, there are an infinite number of bound states that can be possible within our potential well. Right? So what happens when our well becomes more shallow and more narrow? Essentially, our C naught decreases, and there are fewer and fewer bound states present in that well until Z naught is less than pi by 2, where only one bound state remains. Okay? But one thing to notice here is that below Z naught, okay, so there is no case where there are no bound states at all, right? So no matter how weak the well is, there will always exist one bound state of the quantum system. Right? So this is just a pictorial, a graphical representation of whatever I said so far. So next up, this is the second case here. Okay, so for E greater than 0, you have the scattering states. Okay, so essentially to the left of the potential barrier, you have psi of x equals a per ikx plus b per negative ikx. Okay, so and inside the well we have, it's pretty similar to what we had previously. And to the right, there are no incoming waves. Okay, and why do I have these two terms here is that one, this A power ikx is essentially, we can take it as the incoming wave. Okay, and this B power negative ikx is a part of the wave that is reflected off the potential barrier. Okay, and so this psi of x, and this is simply equivalent to what we saw before, as I said. So where here A is the incident amplitude, B is the reflected amplitude, and F is essentially what passes, you could say that passes through the barrier. F is the transmitted amplitude. Right, so this is, again, I'm not going to go too deep into this, okay? It is simply just the boundary conditions that we're using, but with these set of equations, okay? So just take a quick look at this. So this equation 27 is for psi of x at negative a, and this is d psi of dx at a negative a, and the same these two procedure again at plus a and plus a, so we get these four equations. Okay, pretty simple stuff. So using these equations we can eliminate c and d, okay, and we can only solve for b and f. So again, this is just some algebraic manipulation. I'm not going to go too deep into it, since that might be very time consuming, deriving all of this. So I'm just gonna state here that B equals I sine 2LA by 2KL into L squared minus K squared F. Okay, and F is simply this huge thing here. I'm not going to try to read this out because I might have a lot of tongue slip in between. So I'm just gonna state that this is F. Okay. So the transmission coefficient is simply the incident amplitude, sorry, the transmitted amplitude by the incident amplitude. Okay, and we're just going to substitute F and A into this. Okay, so T inverse is simply just equation 33 here. Okay, so this might seem a bit complicated, and it could be because I'm not explicitly, deriving this for you. But then if you just take a look at this and, take a paper and pen and just try to substitute this, it's very simple, okay? So, and when t equals 1, this is another just a simple case. When t equals 1, which means that the entire incident wave is completely transmitted through the barrier, or we could say that the barrier is, the well is transparent. Okay, and t equals 1 whenever sine equals 0. So when this sign essentially is 0, right? So we get t equals 1, right? So then this entire term goes away. So we also make this simple derivation that this term here is simply equals to n pi. So our sign here becomes 0. So where n is just any integer. So now we have seen that we've derived all of this. So from equation 34, we can just say that the energies for perfect transmission then are given by En plus V naught is this term here. As we've seen before, it's right here. It's pretty similar because essentially it's perfectly transmitted. So they're both very similar. And this right here is just a graphical representation of the transmission coefficient and our energy right here of the system. Okay. So next up, we are going to go into our harmonic oscillator problem. Right. So this is a really good example of the different methods we can use to solve problems in quantum mechanics. And there are two ways you can solve this harmonic oscillator problem. So one is the operator method that I'm going to be using right now, and the other is a more analytical method. Okay, so if you can, after this lecture is finished, you can go just take a look at our analytical method, and you'll know how much more simpler this operator method is, and you'll begin to appreciate how efficient and how good operators are for solving problems, a lot of problems in quantum mechanics, not just the harmonic oscillator. Okay, so just a second, I'll be back. 1 second. Let me just get some water. Yeah. So the screen is still visible, right? Anyone?
Yeah.
Yes. Yeah. Okay. Thank you. So you must have begun to see a very nice pattern here, right? So first of all, and you first set up the problem, you set up the equations you have at hand. Okay? You first try to set up the Schrodinger equation and all of your other equations, the differential equations that you can get from the Schrodinger equation. Okay. Next up, you try solving them, which is pretty much the entire problem solving strategy you use in any field in physics, and that is the same thing you do here as well. So now for the harmonic oscillator, we try to solve our Schrodinger equation with the specific potential of V of x equals, sorry, there's not an equal, there should be an equal sign here. So V of x equals 1 by 2 m omega squared x squared, okay, which is the equation for, which is essentially the potential of a classical harmonic oscillator with our uh, with omega being our angular frequency and x being our displacement, okay, or amplitude, sorry. So simply just substituting this into our Schrodinger equation, and imagine this is V of x. So it's a very simple substitution, okay. And then now what we're going to do is we're going to use a small trick here, okay. So then writing this more neatly, so we essentially factor out the half, okay, and we know that the momentum operator, right, is given by this thing right here, h bar d squared psi by dx squared. Okay, so then we essentially use we are writing this in a more elegant form in the terms of commutator brackets. Not essentially commutator brackets, but these are just normal brackets. Sorry, my bad. So we're just factoring out the 1 by 2m outside, and we have p hat squared plus m omega squared x squared is simply psi equals e psi. Okay. So where, yeah, look, this right here. So p hat is simply negative I h bar d by dx. So now you see why we use the square here instead of just p, so that we can get rid of this I right here. Okay. So this is called the momentum operator. Okay, and now what we are essentially trying to do here is we are trying to factor out the Hamiltonian. Okay, so the Hamiltonian is set simply to be 1 by 2m and p hat squared plus m omega x whole squared. Okay, so now simple algebra just says that you can just take this entire term out and then you can call it a day. But then there's a small catch here. We can't just do that because this p right here and this h, these are operators. They're not just some algebraic quantities, or they're not just some value as in say x or m. Okay, so then we can't just take them out of the brackets as easily. So then why can't we do that? Is because these operators do not commute. Okay, so essentially commute, you can take, let's say, x comma p. So then commutative bracket x comma p is not necessarily equal to p comma x in commutative brackets. So that is essentially what we mean by commute. Okay, so here we are going to introduce how do we overcome this problem of this these commutators, sorry, these operators not commutating. We introduce a new quantity, okay, a new operator. So a hat plus minus. You don't need to explicitly know what this is right now. Okay, we'll begin to see its physical significance very soon. So then our a hat plus or minus is equal to is equivalent to this term here. Okay, we're just defining it as this quantity. So then if we take this term, so a hat minus and a hat plus a plus. Okay, so this is essentially we're just using this, okay, a plus a minus, and this pretty much simple algebra manipulation. Okay, so if we simplify equation 41, we get our equation 42, and if we go on, we can write this right here, get this equation 42 elegantly in commutative brackets. So 1 by 2 h bar m omega is simply p hat squared plus m omega x squared minus I by 2 h bar, and this is the commutative bracket that I was talking about. Okay, so x comma p hat. So there is another small derivation here I kind of omitted because I'm pretty sure most of us here know what the canonical commutation relation is. So the x comma p hat is simply equal to ih bar. So we can see here how the ih bars cancel each other, and we have a more simplified term here. Okay, so now we have factored out the Hamiltonian, right? So we saw that the Hamiltonian is yeah, this term here. So essentially we just substitute in h hat for here, and then this is simply just 1 by 2 because the ih bars cancel. Okay. So now again rearranging in for our Hamiltonian, we have this term here, h bar omega in brackets a minus and a plus negative 1 by 2. Okay. So now we have our Hamiltonian in terms of these operators right here. Okay. These are called ladder operators. Okay, and I'll be explaining more about them as we go on. So, and we do the same for the next case. As I said, they do not commute, and so a plus a minus is not equal to a minus a plus. So previously we did for a minus and a plus. Now we're doing the same calculations for a plus and a minus. Okay, and that is simply it's very similar to this, but then I accept this negative sign here, and these two interchange. Okay, so now rewriting this entire thing, we know that Schrodinger equation is simply h psi equals e psi. So then h, we just substituting this entire thing into a Schrodinger equation. Okay, and this is simply just notation. Okay, so a plus or minus and a minus plus, and how you essentially read it is you either take entirely plus minus plus, or you take minus plus minus. Just a simple tip how to read this notation. Okay, so now we make this integral claim here that if the Hamiltonian H psi is equal satisfies the condition E psi. So which necessarily means that H of A plus psi equals to E plus H bar omega A plus I. Okay. Again, there is a small bit of derivation here, a proof, but then this is a proven fact, and I'm just going to take this claim as it is. Okay. So now, let me just give you a small insight of what what the A plus and A minus operators are all about. So then you can take the A plus and A minus operators as they're technically called raising and lowering operators. So what they do is, if you, let's say, act upon, let's say, any wave function or any psi with your operator, what it essentially does is it gives you the next excited state. So if you, let's say, you act the uh, raising operator A plus on, let's say, E naught, you essentially get E1, which is the first excited state. And if you apply that on E1, you get the E2. So then you get the idea, right? So then it's essentially, that's why they're called ladder operators, because you can raise the energy levels and decrease the energy levels just using a simple operator method. Okay, so now applying the lowering operator to the ground state wave function. Okay, so right here we are again making another assumption that if we keep using our lowering operator, okay, so then if, let's say, we use it on psi 0, you technically cannot get negative energy values, right? It has to stop at some point, and that is our assumption that we're making here in equation 48, is that if you apply your lowering operator to psi of 0, it is essentially 0. Okay, so from this we can take psi naught of x, which is simply this equation right here. Okay, yeah, this equation right here. So then we have 1 by root 2 h bar omega is of psi of 0 is 0, right? So this A minus is just this thing here, we're just rearranging it, and then we're getting it for A minus. Or we can, let's say, see from this equation, right, that d psi of 0 by dx is simply equals to negative m omega by h bar psi naught. Okay, again, I'm going to repeat this again. I'm sorry if I cannot completely derive all of this, because you need either a pen or paper, or one of those drawboard uh, appliances that someone like Puber has, but I don't have such facilities right now. So yeah, so I can't be explicitly deriving it. So you're free to derive this relation if you want to. Okay. So again, same thing as I said before. If you solve this differential equation, this is something trivial. Okay, you can just integrate on both sides, and you get ln psi of 0 equals negative m omega by h bar, yeah, h bar x squared plus c. Simple basic integration. Okay, so from equation 51, that is here, we can see that psi naught of x is simply equals to a e power negative this term here. And again, we are going to normalize this wave function right here. So if we normalize that, we have a squared equals root m omega by pi h bar. So from that, we are simply going to just substitute this for a into this. So we get root and then whole squared, root and then one more root again. So you get 1 by 4 m omega by pi h into this term here. Okay. So now if you investigate this, we have that E naught is simply equals to 1 by 2 h bar omega, right? So from here we have our, let's say, our ground state wave function, and we have our ground state energy. So from now on, we're just going to do a simple trick, and we're going to use our operators, right? Raising and lowering operators. Okay, so to get our excited states that are to the nth excited state, we can just simply just use this operator, that is a plus here, acting on this on our psi naught wave function to get all of our excited states of our harmonic oscillator. And same thing for En is that we have this relation here. So En is simply just n plus 1 by 2 h bar omega. So let's say 1, 2, 3, and then it just goes on. And then you get all of our excited state energies in a very, very, very simple method. Okay, so as I said previously, you can go take a look at the analytical method, which has a lot of series and all, a lot of its simplification and all. For myself, at least, this is the most simple way to go about this problem. Right. So next up, we are going to go into the hydrogen atom. Okay. So do not get angry at me at this because I'm going to be like cutting short a lot in this section because I have something much more interesting at the end. That is, we are going to arrive at the same result as this. Okay. So I'm not going to explicitly. Previously itself, I was not really deriving anything. This is going to be very, very simple. Okay, so same thing as before, our potential is simply just E squared by R. And then this thing right here is called the radial wave equation. You can go take a look at it. Okay, this is simply the Schrodinger equation written in spherical coordinates, right? So because if you think about it, the hydrogen atom is simply just one proton and a potential in at the center and one electron essentially orbiting it. Okay, so right now we're trying to find the wave function of the electron, and we can take the proton to be at the center of the origin. Okay, so and we can take that to be pretty stationary. So then the radial wave equation for our electron is simply this equation 59. Okay, so the allowed energy eigenvalues. How do we do this? It's a lot of calculations, but but heuristically speaking, the only allowed energy values for obtaining a normalizable solution, that is, for this equation to be normalized, okay, to be normalizable, we can only have these values of En equals negative me squared by 2h bar squared n squared, okay, which is simply this, which we get this uh, energy here, that is negative 13.6 electron volts, right? So take a good look at this because we are going to come back to this in the next section, okay, where n are just integers and alpha is called the fine structure constant. Okay, so what is the fine structure? We've actually done an entire series, actually an entire lecture on this, right? So the fine structure constant essentially tries to correct for all the spin orbit coupling and our repulsions and all of that, okay, and the essential spin of the electron itself. So they have some, uh, let's say, effect on the total energy levels, right? So then we try to negate the effect of spin and all of that in our energy values. So that is called the fine structure correction. Okay? It's called the fine structure correction. Okay, so now moving on. So now again, this is just a simple. It's not very simple. Sorry, it is just a very bizarre equation right here, which is a normalized wave function for a hydrogen atom. And this is just here for completion's sake. You don't need to exactly know what all of this is. And this L right here, L, 2L plus 1 and all of that. This L is called the Laguerre polynomial, and Y, ML and L. This is called a spherical harmonic. Okay. So again, let's not delve too deep into this, where A is simply h bar squared by me squared, which is called the Bohr radius, okay, which is the radius of the hydrogen atom. So a pretty cool thing that we just found out from calculation, and this has also been experimentally proven. So this is very close to our experimental value, which again, as we said, we essentially predicted a theoretical experiment with our calculations right here. So now there's just a small interlude of what this entire L thing is. So this L is simply just a Laguerre polynomial, which is a solution for the second order differential equation. So xy power n plus 1 minus y dash plus ny equals 0. If you see equation 63, it looks an awful lot similar uh, like this equation here. Okay, because it's d squared and all of that. Okay, so we can see how sorry, no, yeah. So we can see how this can entirely be a solution to this differential equation, right? So yes, a lot of people might be waiting for this last bit here. Pugal was very interested, and Pugal actually told me to do this entire thing about supersymmetry. He sent me a paper, like I think day before yesterday, and he was like, "Oh, take a look at this. It's very interesting. You should definitely do add this to your talk." And I was like, "Oh, okay. Let me try doing this." So, Susie, a new way to solve problems, and much, much more. Okay. So, what is Susie? It's essentially full form as supersymmetry, where it is essentially a mathematical concept, okay, which arose from purely theoretical arguments, which try to unify the forces of nature, right? So, which is one of the main goals in physics. We're trying to, the grand unification of forces. So, supersymmetry was one of the contenders uh, for our endeavors. So, it is a symmetry which essentially relates fermions, which are particles with half integer spin, and bosons, which are particles with integer spin, right? By transforming fundamental particles into superpartners with the same mass and a difference of half spin. So this is just a brief overview of what the big scope of supersymmetry is. But then for this talk, I'm just going to constrain myself to supersymmetry in quantum mechanics. Okay, so physicists essentially tried to find out how the symmetry could be broken because as of now, we have not physically or experimentally observed this in nature. So what we essentially thought was, okay, see, supersymmetry exists and it is being broken. Okay, so which is why we cannot see this in nature. Okay, this search of spontaneous symmetry breaking essentially led us to supersymmetry in quantum mechanics. Okay, so I'm pretty sure supersymmetry has like a lot of calculations and a huge application base. But then I'm very new to this topic, so I'm not very adept at all of the other aspects of supersymmetry. I'm pretty sure some of my friends here are very good, very knowledge in this topic. But I'm just going to talk about supersymmetry, particularly in deriving the hydrogen atom energy levels as we saw before. Okay, so Suzy in QM essentially uses factorized Hamiltonians and partner potentials, which I'm going to explain more as we go on. It's a very effective approximation technique. Okay, so the previous approximation techniques are, let's say, the WKB approximation and the variation principle, the adiabatic theorem. All of them are pretty good approximation techniques, right? But this is even better and much more simpler. Right. So the mathematical aspect, the very basic here is it starts with a general Hamiltonian. Okay. So what do I mean by factorizing our Hamiltonian is we can see that this is a second order differential equation, right? Oh, sorry, our second order derivative here. So we're going to try to reduce the second order derivative to a derivative of the first order. So which will make our calculations a whole lot easier. Okay, so assuming psi naught here, psi naught wave function in question to be nodeless, which essentially means that it vanishes at x equals plus or minus infinity, right? So we can write the Schrodinger equation, especially for psi naught, as equation 65 here, which is 0 equals h bar squared by 2m psi naught d squared by dx plus v1 psi of x into psi naught, which is simply this equation number 64 here. Okay, and because our ground state is nodeless, right, we can solve the Schrodinger for the equation for the potential. V1 of x equals h bar squared by 2m psi naught double dash x by psi naught x. Okay, so you can't see here, where is the simplification in all of this, right? So coming up, so uh, we can now factorize the Hamiltonian as follows. Okay, so we can take the new Hamiltonian, the factorized Hamiltonian H, as A dagger A. So what is A and A dagger, you might ask? A is simply just H bar by root 2m d by dx wx, and A dagger is simply just the transverse of this. Okay, so where wx here is called the superpotential. Okay, we are just assuming two quantities here, and we're going to do our calculations. We're trying to factorize this Hamiltonian. Okay, so Wx is referred to as a superpotential. Okay, so now the relation between our regular potential V1 of x and our superpotential can be found by inserting these factors, right? So inserting A and A dagger into this Hamiltonian. So H psi of x equals right here we have our V1 of x and our Hamiltonian, right? So we essentially substitute it back into our equation. So H psi of x equals this right here, A dagger A psi of x. Okay.
Uh, there's a small correction. I think
Yeah.
you wanted the factorization to be
Mm-hmm.
my bad. You wanted the factorization to be d of dx plus minus w of x. I don't think it's a product. I think it's a summation.
So summation.
Yeah, it should be
Yes.
d of dx plus w of x
Okay. Okay.
and d of dx minus w of x.
Okay. Okay. Plus w of x. Okay. Okay. I get what you mean. So right here, right? So you're trying to factorize.
Yeah. D of dx plus
Ah,
w of x and minus d of dx plus w of x.
okay. 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 So I think there might be a small correction there. So thank you. Who's this again? Nekoma, right?
Yeah.
Yeah. Yeah. Thanks, man. So then, as Nekoma said, it's right here is d of dx plus w of x. Okay. So that is essentially what we're trying to factorize here. So thanks for that correction. So I think it also applies here. Okay, so we are essentially substituting those values back into the Hamiltonian and simplifying and cleaning up this gives us v of x equals w squared minus h bar by root 2m w dash of x. Okay, this is called the Riccati equation. I'm pretty sure I'm butchering that name, but then so the Riccati equation. So now solving for the superpotential w of x. Okay, so we saw v of x right here. So v1 of x is this. And essentially now solving for the superpotential, we have w of x equals negative h bar by root 2m psi naught dash x by psi of x. So now we have seen here that we have essentially reduced this to a first order derivative and not the second order derivative. So now we are now going to do the same, but for instead of a dagger a, we are going to do for a dagger. Okay, so the same equations right here. So we calculate v2 of x, which is essentially, if we see here, it's right here, yeah, w squared minus this term here. Here is just a w squared plus this term here. Okay, so this is called a supersymmetric partner potential of v of x. Okay, so now that we saw all of our mathematical aspects of this, let's try to now use this in our hydrogen atom problem. Okay, so the same Coulomb force potential and the same radial equation as we saw before, right? So then essentially now substituting this into this, we have the shifted radiate potential, that is v tilde r is this huge term here, right? This huge equation. So take a look at this and we'll move on. Yeah. So now we begin to find the corresponding superpotential, right? As we saw here, v of x, we're trying to find out our superpotential v tilde r equals w r squared minus h bar by 2m w dash r. Okay, so making the answers w r equals c minus d by r, right? So there's a lot of calculations here. I kind of cut it down a lot. So substituting and simplifying this gives us these constants. You can essentially just substitute and find out. Okay, so if you substitute and simplify this, you essentially get w of r equals this entire term here. Okay, so now we found our superpotential. Okay, so naturally our next step here is to find our partner potential. But before that, we can see that the ground state energy of the radial Hamiltonian is E naught equals negative c squared. Okay, so I didn't explicitly give out the value of c here, but then you can see that let's see that minus c squared is equal to this huge term here. Okay, and if you just substitute the values here, you can see this value that this entire thing approximates to negative 13.6 electron volts. Now, if we go back, that is exactly what we found out here, right? Which is negative 13.6 electron volts. So we can see that this approximation is very close to what we got previously, right? So, and why is this more elegant, you might ask, is because the previous thing that I showed, the previous section of the hydrogen atom, pretty much looks simple, but then if you actually calculate that, it takes pages and pages of derivation. But right here, we just directly just factorized. We found out the superpotential, and now we're going to find out the partner potential from equation 72 right here. Yeah, we are going to use W and W dash to find out our partner potential. So V2 of R is simply just, not simply, it's complicatedly this huge term here. Okay. So, and here another thing we are going to look into is that the potential shape invariance, okay, is satisfied. And I'll show why that is satisfied in the next slide. And we can see that it is satisfied because when we compare our two potentials, our partner potential and our initial potential, it obeys this condition right here. Okay, so what is this condition in, let's say, a graphical format? We can see that essentially the two shapes here are similar, right? They're just shifted. Okay, so that is why they're called shape invariant potentials, or we call them as SIPs. Okay, so for two partner potentials to be, let's say, if they are to be correct, or yeah, to be correct, they need to obey this shape invariance. Okay, so now we have checked that graphically, if we plot V1 of R and V2 of R, we can see that they are both SIPs. Okay, so now we've verified that this partner potential is correct. Now we can go on to seeing that the relation between the two parameters, let's say A2 equals FA1, is simply the difference. What this entire statement tries to say is that I differs by this quantity right here, which is L plus 1, right? Because if we see this potential here, we have L plus 1, L plus 2. And previously, if we see that we have our L plus 1 here and not an L plus 2 term right here. So that is essentially what we're trying to say, is that these two parameters are essentially separated or differ by this L plus 1 quantity here. And our remainder, okay, so essentially this plus RA1, so we essentially call this the remainder, which essentially shifts this potential. We essentially call this as RL, okay, which is this term right here. Okay, so I'm not going to try to read that. Okay, so, and this remainder, so this remainder right here is equal to the energy gap between our ground state or zero energy level and our first excited state. Sorry, it's not ground state, it's our zero energy and our first excited state. So E delta of the difference between our zero energy and our first excited state is essentially this thing right here. So from this, how do we find out our ground state energy? Okay, since ground state energy is not non-zero, so now we're going to shift down this our first excited state with our this remainder here. So essentially, our E1 is this term here plus our remainder. Okay, so E1, I think I might have derived previously. So E0 is right here, right? So essentially, we're just finding out our E1 by adding this remainder right here. Okay, so we found out our first excited state. Okay, so now if you generalize this to the nth level, I think there might be a small correction. I think this is the E0 or E1, I'm not so sure. I'll check and get back to you. So yeah, now generalizing this to the nth energy level, En, it's simply just E0 plus this entire term here, which is summation n by n to I equals 1. So essentially what is this? This is very similar to our ladder operator method as well, because we are simply just adding this extra remainder to our energy level to get our successive excited states, okay? So for L equals 0, right, for L equals 0, we have our En to be just simple thing here. E power 4m is simply just 32. E power 4m by 32 pi square h square e epsilon naught squared in brackets n plus 1 whole squared. Okay, and this thing right here is the known formula or the calculated formula for energy levels of the hydrogen atom. And if you actually substitute the values in this thing, in this equation right here, you get the precise energy values of each excited state as we have practically observed. Right, so I think that is the conclusion. So thank you, and any other points to be made, we can have a discussion, a short discussion. Any corrections in this, I'm open to any discussion. Yeah.